Good afternoon, my name is Martin Knoblauch and I work for Indicen. Today I want to talk about libraries, but let me say a few words in Spanish first. Quienes prefiráis seguir la presentación en español, tenéis las transparencias disponibles en mi página web. ¿Vale? Podéis bajarlas con el móvil incluso y, en fin, probé y funciona. Sigo en inglés. If you prefer to follow this presentation in your computers, you can download the PDF in Spanish or English. I want to talk about library interfaces and why are they so horrible in many senses, why are they so unusable sometimes, and how to make them more usable with a reasonable effort from the developers. So there is a previous talk. I tested this first in the Madrid C++ meetup, and I took many things out of the presentation. It was too long, so you can view the previous version if you are interested. It contains general advice about project structure and libraries and, well, probably things that the experts already know. So I wanted to keep this short list of recommendations. Don't use singletons, raise the level of warnings, keep your compilation free of warnings, use const where it proceeds, choose wisely whether passing by value or reference, and consider compilation and move semantics. And this last one changes the two previous ones. So if you don't know about move semantics, read about it because it changes the rules about using const and passing by value or by reference, and it can simplify your code a lot. Use RAII, resource acquisition is initialization, use exceptions, use the guideline support library, read the core guidelines, the core CPP guidelines, which are on the internet. Use units and user-defined literals, choose wisely between pointer, reference, and smart pointer, and consider the problems of binary incompatibility and separated heaps, which motivate this talk, which I'm going to talk about now. So the potential binary incompatibility means that you might build a library using some compiler, some version of the standard, and some specific implementation of classes like string and vector, and then ship it. And if you expose these classes in the interface, your user, your client, might link your library, but his compiler might not have the same string and vector implementation. They might be different. They might have a different layout in memory, bit by bit. And that's a huge problem. Also, in Windows, sometimes, depending on how you link your library and how your client links the library with the program, the heaps might be separated so that whatever is new in one side cannot be deleted in the other side. It must be deleted on the same side where it was new. And these problems can have subtle forms. You can make mistakes without clearly doing a new and a delete on the other side. You might pass a string by reference, and the other side might modify that string, and modifying a string might require an allocation. So bad things can happen. What happens with a lot of good C++ features that we like to use? So a good solution is to have all the sources, recompile everything every time in your compiler, and everything is okay, that's great. Or at least, if your library provider is ready to compile the library in every specific version of the compilers, including future versions, and ship them and give them to you, you can manage that. And you can use Conan to manage all those dependencies, and that's great. But in general, sometimes you cannot do that. Another nearly perfect solution, sarcasm intended, is the hourglass pattern, which suggests implementing your library internally in C++, then offering all your functionality through a narrow, castrating, pure C interface, and then putting an additional C++ layer on top of that to provide C++ objects to your client. And that additional C++ layer would be header only, so that it would be compiled on the client's side. But this takes a lot of work on one hand, and it doesn't scale. Okay, so you see here the headers are compiled on the client side, so everything is fine. So what if I use another library, which depends on the first library, and then this other library wants to share objects with the program, with the final client? Can I share these objects of the additional C++ layer? No, because the other library and the client might be compiled with different versions of the compiler, and that's not compatible. So the other library should offer another hourglass implementation and pass through that hourglass its own objects plus the objects of the first library. So that's why I say it doesn't scale. It's a lot of work and it doesn't scale. So my proposal is, let's use C++. Let's come out of the closet and start using C++ on interfaces as well, not only in our implementations, because otherwise this doesn't scale. We cannot compete with other languages. We should use C++. Which parts of C++? Well, we can base our interfaces in very stable binary types, and we'll see. And we can use smart pointers, not in any way, but we can use some smart pointers. Is this a replacement of the hourglass, what I am proposing? Maybe. Maybe you can take it as a more attainable solution, or you can take this presentation as a first step prior to the hourglass, if you choose to. Anyway, what I am going to tell applies anyway, if you are planning on using the hourglass. So, smart pointers, let's dive in. Can we use them in the interface, and which ones and how? Shared pointer. For example, can we pass a shared pointer through the interface? It contains a pointer to the deleter, which is fine, because when the object is deleted, the delete will be called on the right side, on the library side. If the library makes the new, then delete will be called on the right side. But it has inappropriate semantics. When you pass a shared pointer, the one who receives it will suspect who else has a pointer pointing to this object. Who can modify it? Can I count on this object not being modified? Can I modify it without affecting others who might read the same object through the same shared pointer? So paranoia grows, and at some point the client says, oh, I'll make a copy. And that's precisely what we didn't want in first place. Also, shared pointer has a cost in memory and time. It's a small cost, but it can be measured. It's a cost. And there are chances of binary incompatibility because smart pointers are quite complex. They have counters of strong references and weak references. They must have either a mutex or these counters be atomic. So it's relatively complex. Let's see unique pointer. Can we pass through unique pointer? The semantics are almost perfect, because when you pass a unique pointer, you give away the object. If you pass a unique pointer, the one who receives it might delete the object immediately. The object might cease to exist immediately. So the one who is giving it cannot count on the object being alive for any longer. And this somehow guarantees that the one who receives the object knows it belongs to him. He can modify it, he can count on others not modifying the object, and so it's the right semantics. And there are very few chances of binary incompatibility because inside it's just a pointer. It's just a structure containing a pointer. The problem is it does not contain a pointer to the deleter, so it doesn't solve every problem. But luckily we have unique pointers with a custom deleter. We can specify with a pointer to function which function should be called to delete the object. So the cost is reasonable. We pass a structure or a class with 2 pointers inside, which has very few chances of binary incompatibility as well. Alignment is the same for the 2 pointers. There probably will be no gap between them. So the cost is reasonable, and the only drawback is that the syntax is a bit tricky. That thing up there might seem strange for those who are not used to pointers to functions, but it's not so bad. And we have syntax sugar. We can type def the type of deleter. This first type def would be a declaration of a function without the type def. With the type def, it declares a type of function, the type of function that deletes things. And the second type def defines the type of unique pointer that I want to use, a unique pointer that points to a thing and contains a pointer to a deleter. Easy. So this would be a function in the library, creating an object, creating a thing, and returning it for the client. It would construct one of these unique pointers, call new to create the object, and in the deleter, I would put this lambda, which is a function that receives a thing and just deletes it. And these 2 pointers, the pointer to the thing and the pointer to the lambda, are embedded inside the unique pointer and returned to the client. So it's perfect. When the last owner of this unique pointer doesn't move it but lets it die out of scope or whatever, this lambda is called. And this lambda is code in our library. So it's perfect. And the other way around, we could create a function in the library to consume a thing. This function would receive the unique pointer as a parameter. The color should move to pass the unique pointer. And now we can decide whether to store the object, move the unique pointer to somewhere and keep it, or let it be destroyed as p goes out of scope when the function ends. Compatibility. These pointers are not compatible with ordinary unique pointers, and that's good, because it would be a mess. And on the other hand, we can mix pointers to objects created at both sides. The client might create pointers to things on his side, and if he puts the deleter right, he can pass the unique pointers to the library. Here is an example. We create one thing and other thing calling the library. The library creates the 2 objects and returns the unique pointers. And then we create a third thing, another, in the client side, and specify the deleter with a lambda, just as before. Now we can pass one and another to the library, and the library does whatever it has to do. When it ends with these objects, it will call the deleter of one on the library side and the deleter of another right here on the client side. and we would destroy other when going out of scope. Well, variants of this, not C++ variants. Well, I don't recommend doing this, but we can do it. Since we are specifying a pointer to the deleter, we can point to whatever we want. We can customize it. For example, we could return an object which is not allocated dynamically, and the deleter would point to a no operation function like this, and everything would work. Other than we are using a singleton here, which is horrible. We are breaking all the rules, and and the caller might believe that he owns the object, but that unique pointer is pointing to a shared object. Don't use singletons. We can specialize this for arrays with modern C++. We just have to use the square brackets in new and specify the number of elements. And remember, use the square brackets also when calling delete, and everything will be fine. If you use a very old compiler, maybe you cannot specify the square brackets in the unique pointer type. You would need to call get and then the square brackets, and well. And just as we have make unique, we could make our own make cross for these type of pointers, which is very handy. And if you use a very old compiler, you would need to use variated macros, which are horrible and not worth wasting time. Custom deleter at zero cost. This is another variant, a very interesting variant. We can save that pointer, that extra pointer, by using a function object, a functor. Instead of a pointer to the deleter, we can specify a class with the parenthesis operator overloaded, and that function would do the delete. The problem is you can use this only in one direction, in the sense that this functor must be in one side, and it has to be the library, because the library doesn't know anything about the client when compiling. So it has to be in the library side. But objects can travel in both directions. It's just that if you do this, you must new them always on the library side. Let's see how we would do this. Let's make a custom deleter for two types, thing and blob, in our library foo. First, we would declare the generic deleter, and note that I am not implementing the delete here. It's not in line. Now we would provide an implementation for the deleter, but with these horrible macros, we prevent the client from seeing this code. This code is only in the library. Then we can instantiate our generic deleter for the two type of things. And thanks to these horrible macros, this is just a declaration, an external declaration for the client. This is the only way I found to do this, making it cross-compatible, working with different compilers, platforms, whatever. And finally, we declare our unique pointer type, which can be templatized, and our functions providing things and blobs. Macros. The macros I showed before, for completeness sake, I included them in the presentation, but I don't want to waste time on this. It's the typical stuff you know if you use Visual Studio. That does for you, and a bit more, but that's it. Let's see an example. This is my first attempt to to create an example class that a library might pass to the client. Okay, it would be a message containing numbers and text. And I include string, vector, etc., macros, and this is our class. The class would contain the vector and the string as data members, and the client will see this declaration. The client's compiler will believe it knows the internal representation of this object, but it will do no harm because the constructors are private, the destructor is private too, and we have the deleter here. We can put it inside the class better than outside. And now the public stuff, we can offer an assignment operator, copy and move assignment. We can offer a swap function. Once the client has the objects, it can call these functions. The problem is creating the objects, creating and destroying the objects. But these we can expose. And here I am defining a couple of types. The unique pointer, of course, and I wish it was a span. These pairs of pointers, I wish I could use span instead of these pairs of pointers. But out of the two implementations of the GSL that I've looked, one of them stores spans as 2 pointers, and the other stores spans as a pointer and an integer, a signed integer. And this is going to change, I believe. The news they are changing span to be unsigned. The size will be unsigned, and so we will have a third binary representation of span.
We'll see.
We'll see. Okay, let's grill the committee later. At last, the class can offer these factory methods instead of the constructor, so the client is forced to call these create functions. They'll return unique pointers, and that's it. Finally, clone, which replaces the copy constructor. Not nice, but finally, a few accessor methods using const char star for strings and our pair of pointers for the numbers. So at some point, this is C. This is as horrible as the thin part of the hourglass, but the lifetime of objects is managed in more user-friendly and, well, many other things. Finally, asymmetric swap exposed for the user, and yet another version of the same thing. The thing is, I always thought, well, I could use the pimple idiom. Do you know the pimple idiom? I could use the pimple idiom, but it would add an extra level of indirection. That's what I thought all the time, so at start I didn't use it. But when I started using the pimple idiom, it turns out that I get a friendlier interface, and this level of indirection does not add. It replaces the other level of indirection. That is, I can declare my new class. This time I don't need to include string and vector, which is much cleaner. Here, inside my class, the only data member is the pimple, the pointer to implementation, which is a unique pointer. I defined a deleter, but in reality, I don't need the deleter because the destructor must be in the CPP, so I don't really need the deleter. Oh, in case you don't know the pimple idiom, the implementation, the thing that is pointed by this unique pointer, is a structure which I only forward declare here. I'm not providing the internals of the structure. And the structure is defined in the CPP file, so that only that file can handle can access the implementation. So I can provide all these nice constructors: move, copy, default, the swap function. Now I don't need to expose my unique pointer type because it's private. So I only need these pairs of pointers, non-const and const. And now I can provide constructors taking the string and the numbers. Again, the numbers with a couple of pointers and the string with a const char star. Finally, the same accessor methods and the symmetric swap. And that's it.
Questions?
Hello. Are you sure that the ABI of unique pointer is compatible with every compiler from now to the future? Because if it isn't compatible, then this breaks out.
Completely right. No.
No.
Well, I don't expect any change. I tried with the last Visual Studio 2019. Unique pointer still has the same size. I wouldn't expect them to change it. I believe they also want their new versions of the compiler to be compatible. So if we had unique pointer and span fixed in terms of ABI, that would be great. True. Yeah. Oh no, just one more thing. If we didn't get them standardized in terms of ABI, we could write our own. Imagine writing your own span and unique pointer so that they are more stable than the standard itself.
Well, we do not have any ABI problem with span because currently we have no span.
Right. It's not yet in the standard. Right. But when you get into the standard.
What? No.
Sorry.
Just want to make a point about ABI. Just want to make a point that the vendors, most specifically Microsoft, goes through tremendous lengths and discussions to keep ABI compatibility as much as they can. So since 2012, you're probably not going to find ABI incompatibility, specifically Microsoft products. Mm-hmm. And of course, Clang, GCC, even like XLC goes through great lengths.
Great. Thank you.
But at the same time, we cannot standardize ABIs.
Correct.
There was, interestingly, the only attempt to standardize ABI or to discuss a standard ABI was presented by Microsoft, and it had an overwhelming rejection. Mm. So it seems people is not interested in standardizing ABIs. When we make changes in the interfaces, we keep an eye if this could eventually cause an ABI breakage. Mm-hmm. That's a different issue.
Maybe they try to standardize too much. I mean, if you could. No, I mean, if you could.
I always hear
if you could standardize
the complaint other way around.
If you could standardize string and vector, that would be a dream come true. But I understand this will not happen. But unique pointer is much more simple.
I mean,
it's a pointer.
we made a major change with string that caused a lot of ABI breakages in 11. And I don't think we want to repeat that experience, at least not frequently.
Okay, thank you.
More questions? Come on, I know that you are hungry, but probably. And I'm told that you have to wait 10 minutes to get the food anyway, so more questions?
Thank you. Also, thank you for the presentation. Specifically, I would want to ask, how would you deal with vectors and strings? I noticed that in this case of strings, you return a char pointer, a C interface. But what would you do if you want to return an array of something? Of course, you could return a unique pointer to an array, but you also need the length. So, what kind of solution do you see for this?
Span for an array. Span.
Okay, span could work.
Two pointers, or a pointer and an unsigned.
Yeah.
Come on, no. I cannot resist to say something about unsigned because everybody is wrong. So, anything where you have any arithmetic operation, if you use unsigned, you are wrong. Yes. Unsigned are not natural numbers. For everything that you perform, an addition, a subtraction, a multiplication, use int. The standard library is broken because all the containers return a size as size t, which happens to be an unsigned. And this is a big mistake. And is useless because in any way, I don't know if you know or not, you think, okay, but with size t, I have one more bit, my vector could be larger. No, it can't. You cannot have a vector whose size is more than half of the representation of your integer type anyway. So you are wrong. I'm sorry. And the standard library is broken. So unsigned is nice when you have a bit pattern and you are performing bitwise operations. Okay. I cannot imagine much more uses than that. And this, we really need to fix this in the standard library. But anytime that you return a size, please return a signed int or a signed long. Well, we are still fighting with that. So, sorry, I could not resist.
I understand.
Now, one more question. No question? Okay, you are free, but you will have to wait like 5 minutes to get the food. Okay. So,
Thank you.